There's a garage attached to a small ranch house outside Tulsa, Oklahoma, where something quietly strange has been happening for the past 3 years. Every month, the electricity bill arrives, and every month, the number on it is almost embarrassingly low. Not because the family stopped using power, not because they installed expensive solar panels on the roof, not because they signed up for some special utility program or government rebate, just because of a simple wire antenna mounted to a wooden post in the backyard, connected to a small circuit board sitting on a workbench inside. The first time the owner showed me the setup, I genuinely didn't understand what I was looking at. It looked like something a high school student built for a science fair. A length of copper wire, a handful of electronic components, a small rectifier circuit soldered onto a board. Nothing impressive on the surface, nothing that looked like it should be doing anything meaningful at all, but it was pulling energy out of the air. Not solar energy, not wind energy, radio frequency energy. Electromagnetic radiation that already exists everywhere around us, broadcast constantly from cell towers, radio stations, television transmitters, Wi-Fi routers, and dozens of other sources that blanket modern civilization in an invisible sea of electromagnetic waves. And with the right antenna and the right circuit, some of that energy can actually be harvested. That's the part that stopped me cold, because most people assume that getting electricity requires either paying for it from the grid or installing an expensive generation system on your property. But electromagnetic energy harvesting, sometimes called RF energy harvesting, doesn't fit neatly into either category. The energy is already there. It's already traveling through the air. It's already passing through your walls, your yard, your body. The only question is whether you have a system capable of capturing even a small fraction of it. And right now, that question is becoming surprisingly relevant. The principle behind RF energy harvesting is not new. In fact, it goes back over a century. In the early 1900s, experimenters discovered that certain antenna configurations connected to simple rectifier circuits could pull enough electromagnetic energy from AM radio broadcasts to power small devices without any battery or external power source. These were called crystal radio sets. Children built them from spare parts. They required no batteries. They required no power outlet. They simply captured energy already moving through the air and converted it into sound. Most people today think of crystal radios as toys, historical curiosities, but the physics underneath them never went away. And in recent decades, electrical engineers at universities and research labs started taking that same principle seriously again, this time applied to modern electronics and modern electromagnetic environments. The difference between 1920 and today is enormous. In 1920, the electromagnetic environment was sparse. A few AM radio transmitters, some telegraph signals, not much else. Today, the situation is almost incomprehensibly different. Cell towers transmit continuously across virtually every populated area in the country. Wi-Fi signals fill homes, offices, coffee shops, and parking lots. FM radio, television broadcasts, emergency service transmitters, GPS satellites, Bluetooth devices. The modern electromagnetic environment is thousands of times denser than anything early radio experimenters ever worked with. And that density matters, because more signal means more harvestable energy. Researchers at Georgia Tech published studies demonstrating that RF energy harvesting circuits could power small wireless sensors entirely from ambient electromagnetic radiation in urban environments. Engineers at MIT and several European universities explored similar concepts for powering low-energy IoT devices without batteries. The Defense Advanced Research Projects Agency funded research into RF harvesting for remote sensors that could operate indefinitely without power infrastructure. None of this made major headlines, but the science was real, documented, and quietly advancing. Now, here's where things become practical. Because most of that university research focused on extremely small-scale applications, tiny sensors, wireless monitors, medical implants. The energy densities involved are genuinely small. A well-designed RF harvesting antenna in a typical suburban environment might capture enough power to run a small LED, charge a watch battery over several hours, or keep a low-power sensor transmitting data. That's not nothing, but it's also not powering a refrigerator. And this is where honesty matters. Because the internet is full of videos and articles claiming that a simple wire antenna can slash your electric bill in half or run your entire house off free atmospheric energy. That is not accurate. That is not what the physics supports. And anyone telling you otherwise is either badly misinformed or deliberately misleading you. What a $25 antenna setup can genuinely do is more modest and also more interesting than the exaggerated claims suggest. One retired electrical engineer I spoke with outside Knoxville, Tennessee, spent 2 years quietly experimenting with RF harvesting circuits in his home workshop. He wasn't trying to eliminate his electric bill. He was trying to understand what was actually possible with simple, inexpensive components. His conclusion was measured but genuine. He said, "The technology is real, the energy is real, but the expectations have to match the physics." What he built over those 2 years was a series of small harvesting arrays, multiple antenna elements connected through rectifier circuits and small capacitors, feeding into low-voltage storage systems. The setup cost him roughly $30 in components sourced from online electronic suppliers and a local ham radio shop, and it reliably powered a small cluster of LED lights in his workshop. Continuously, without any connection to the grid, without any solar panel, without any battery replacement. That's worth pausing on. Continuous low-level lighting from ambient electromagnetic energy, for free, using a system that cost less than a dinner out. The circuit itself is not complicated. At its core, an RF harvesting system consists of 3 main parts. First, the antenna, usually a length of wire cut to resonate efficiently with specific frequency ranges in the local electromagnetic environment. AM frequencies, FM frequencies, and cellular frequencies each respond to different antenna lengths, and experienced builders often combine multiple antenna elements to capture energy across a broader spectrum. Second, a rectifier circuit, typically built around 1 or more Schottky diodes, which are specifically chosen for their ability to respond to very small, high-frequency signals more efficiently than ordinary diodes. Third, a storage element, usually a bank of capacitors or a small rechargeable cell that accumulates harvested energy over time before releasing it to power a load. The components are ordinary: Schottky diodes, capacitors, copper wire, a small circuit board, all of it available for a few dollars from standard electronics suppliers. And the assembly, for someone with basic soldering skills, takes an afternoon. But the performance depends enormously on location. This is the part most online guides underemphasize. A harvesting antenna mounted on a property 2 miles from the nearest cell tower in rural Montana is going to perform very differently from the same antenna mounted on a rooftop 1 block from a dense urban cell array in Chicago. Signal density matters, proximity to transmitters matters, antenna orientation and height matter. One builder in suburban Dallas who documented his experiment online found that simply raising his antenna from ground level to rooftop height nearly tripled his harvested power output. Another experimenter in Portland discovered that orienting his antenna array toward the nearest cell tower cluster increased yield significantly compared to a randomly pointed installation. These details are not magic. They're just basic antenna engineering applied thoughtfully. And the people who get the most out of these systems are usually the people who approach them the same way the flywheel builders approached mechanical storage, not with grand expectations, but with patience, curiosity, and a willingness to iterate. There's a quiet community of RF harvesting experimenters scattered across amateur radio clubs, electrical engineering forums, and off-grid homesteading networks. They share antenna designs, rectifier circuit improvements, and field measurements with the same practical mindset that characterized generations of workshop tinkerers. Not trying to break the laws of physics, just trying to extract maximum usefulness from the physics that actually exists. And what they've collectively learned is genuinely useful. Simple single-wire antennas perform adequately, but leave a lot of energy uncaptured. Folded dipole configurations improve efficiency. fractal antenna geometries, complex branching shapes that resonate across multiple frequencies simultaneously, have shown notable performance improvements in several documented experiments. None of this requires exotic materials or expensive manufacturing. Paper, copper tape, and basic soldering skills are sufficient for fractal antenna construction. The storage side has also evolved. Early simple circuits fed directly into a single capacitor, which charged quickly, but discharged just as quickly. More refined designs use supercapacitors, components that store significantly more energy than standard capacitors and release it more smoothly. Some builders stack multiple supercapacitors in series to build up enough stored voltage to run practical loads. Others incorporate small boost converter circuits that step up the low harvested voltage to levels sufficient for standard electronics. Again, none of these components is exotic. All of them are available online for a few dollars each. The honest picture that emerges from all of this experimentation is straightforward. A well-designed, carefully located RF harvesting system built for $25 to $30 can realistically power small, continuous loads. LED lighting, low-power sensors, small charging circuits for handheld devices, emergency indicator lights, and remote monitoring equipment. It will not power your air conditioner. It will not replace your utility connection. It will not make your electric bill disappear. But that's not really the point, and once you understand what the point actually is, the technology starts looking much more interesting. Because what RF harvesting represents isn't a replacement for conventional power. It's a different category of power entirely. Free, ambient, continuous, infrastructure-independent energy for small but genuinely useful loads. Energy that requires no fuel, no sunlight, no wind, no maintenance in the conventional sense. Just a wire, a circuit, and the electromagnetic environment that modern civilization has accidentally created around itself. One ham radio operator outside Columbus, Ohio, put it simply. He said we spend billions building wireless transmitters that flood every populated area with energy. And then we pay for electricity to run tiny devices that could theoretically harvest a fraction of that energy for free. The inefficiency of that situation, once you notice it, is hard to unsee. And that's what makes this story bigger than a $25 science project. Because right now, energy costs are rising. Grid reliability is declining in parts of the country. More people than ever are thinking seriously about partial energy independence for small but critical loads, emergency lighting, communication equipment, monitoring systems, and low-power backup circuits. And the barrier to experimenting with RF harvesting has never been lower. The components cost almost nothing. The physics is well documented. The community of people sharing knowledge is active and accessible. It won't power your house. Nobody serious is claiming it will, but it might power something useful. Continuously. For free. Using energy that's already passing through your walls, whether you capture it or not. And in a world where every kilowatt hour costs money and every system seems designed to be replaced rather than understood, that's a genuinely interesting place to start.